All right. Yes, we'll get started right now. Good morning, everyone. My name is Mohammed Nasif. I'm a third-year PhD student, Georgia Tech, and I'm also one of the graduate student members of SASAC. So welcome to the lecture three of the For Students by Student series. This lecture series is a new initiative of SASAC for the student community to engage in gaining new knowledge and to familiarize with frequently used tools. The FSBS lecture series will focus on sharing minor technical skills/knowledge across the students from undergraduate to graduate level that can be utilized in coursework and/or research. Each lecture in this series will be developed and delivered by a graduate student with considerable experience in that area, tailored to AE applications. These lectures will have a new topic every month or every 2 months based on a suggestion by students. So in the past, we have had MATLAB OD45 and SysML. Today, we'll be doing an introduction to STK by Ulysses Eduardo Nunez. He's a graduate student in the Space Systems Design Lab at Georgia Tech. Originally from Santiago, Panama, Ulysses has completed his BS and MS in aerospace engineering from Georgia Tech as well. He has been a TA for senior design for 2.5 years, so he has considerable experience in teaching STK. His research interests are in the areas of astrodynamics and spacecraft guidance, navigation, and control under Dr. Lightsey. His current work encompasses applications of probability theory and quasi-random number sequence generation to spaceflight mechanics, specifically in the context of dynamics of spacecraft relative motion. These techniques are applied to the process of collision avoidance in spacecraft formations, collision risk quantification, collision risk interpretation, and reduction. So before I hand it over to Ulysses, just want to let you know that questions are welcome during this talk. You can put your questions in the chat, and while Ulysses will be sharing his screen and giving the presentation, I'll monitor it and I'll interrupt him in the middle with your questions. So with that, I hand it over to Ulysses, and you can share your screen now, Ulysses.
Thank you, Nasa, for the introduction, and quite the honor to get to speak to you guys. Are you guys able to see my slides? Hello? Can you see the slides?
Yes, we can. Sorry.
Okay, cool. So first of all, what is STK? STK is a tool that stands by Systems Toolkit, developed by the company Analytical Graphics Incorporated, or AGI. And STK is basically an environment for modeling the motion of objects in space. And so this little animation that I have on the right kind of illustrates the idea of the different moving parts in STK. So first of all, we have a central planetary mass. It can be a planet of your choice. It can be the sun. I guess I don't see any reason for modeling things beyond that, but you also have objects that are in the planetary mass or on it, like for example places or sensors that are earthborne, and then objects that orbit the planetary mass, like satellites, namely, and other things like that. And there's other objects like perturbing masses and things like that. And so what the main thing that STK does is that it allows for the propagation of the motion of the objects in space, and for the computation of the relative geometry between those objects and between things that are like attached to the planet of your choice. And so as you can see, something with this much generality has a lot of applications, as you'll see in this talk. The applications are very, very general, and so we can use this tool for the entire life cycle of a space mission, named from trade studies to decide what the mission is actually going to be, to detailed orbit design and things like that. A lot of preliminary design, and also for analysis of past missions, because it allows for you to access planetary ephemeris for the past. I'm not sure how long, but at least for the 20th century and into the future as well. And so as a Georgia Tech aerospace engineering student, you have access to it. we're going to do this talk in Vlab just because I wasn't able to get a local install of it. But if you do that, I mean, that's fine. You don't need to have any kind of local installation. The cons is that it's slower and you do need a stronger internet connection. If you're able to do a local install, that's going to be much faster, but it's going to need a lot of space. And so this talk isn't going to be super technical. It's more going to be pertaining the application of it, just kind of motivating why using STK is cool, why it's awesome, why you should do it, and why it's good for you. And I guess in the meantime, we'll talk a little bit about also how to use it at a high level. And if you have questions toward the end, feel free to ask. And also, if during the presentation you have questions, please feel free to submit them in the chat box, because this is primarily a tutorial, so we want it to be as interactive as possible. So if you're on campus, please go ahead and log into Vlab to mycloud.gotech.edu and open the aerospace engineering virtual machine. That way you can follow along. And if not, Nasif is going to post this online so you're able to follow along. And again, if you have questions after the talk, we can go into those in more detail as well. So we're going to do 3 quick tutorials. So the first tutorial is going to pertain with creating a scenario. We're talking about basic satellite sensor access from a sensor on Earth to a satellite in space. And we'll see some examples of that, as well as some worked out examples. We're not going to build up to those, but we're just going to see the finished example. In the second tutorial, we're going to look at choosing other planets. We're going to focus on the scenario focus on the sun. And at that point, we'll show different examples for interplanetary orbit transfers from like Earth to Mars, which is really relevant right now with the launch of Mars 2020, the Perseverance rover, and the different launches that have been happening from the United Arab Emirates and Europe and stuff like that. And those places, they've all been launching probes to Mars. And so we'll focus on that example, actually. And then our last example, we're going to look at multiple satellites and what happens when you have different dynamic models. And then the application that we'll see is orbit insertion in the Mars environment. And we'll finish with looking at a Mars flyby video for a flyby of Phobos, which is actually a moon of Mars. And whatever we have time for, I have a different separate presentation prepared in case we finish this early, and we'll go over that. So please help. Please feel free to ask questions as we're going on that. All right, without further ado, this is the example that we're going to look at, the tutorial for accessing for basic satellite sensor access. All right. So let's see. We're going to share the screen for Vlab right here. 1 second, please. Screen. So you are able to see Vlab now?
Yep.
Okay, cool. All right, so what you do is that you just go to the search bar and type STK, and the latest installation that we have is STK 12. And so we're just gonna continue real quick, and it takes a little bit to load. And something that you should try to keep in mind is try to save as much as you can, because STK can be a little bit finicky. All right, so first thing we want to do is in View, come to View and hit here Planetary Options in order to be able to pick a planet of our choice. So now we can input a scenario name, just something descriptive. In our case, we're going to say SASAC tutorial number 1. And it allows you to pick a date, a date and time with Gregorian hours. So, for example, this is February 25th at noon Eastern Time, or 5 p.m. Universal Time Coordinates, or Greenwich Time. And so at that point, STK is going to load itself and going to load the central planetary mass. And so at this point, Earth is going to be the center of our reference system, and most of the force models that we're going to use are going to be Earth-centric. And so here, the first thing that we can do is insert a satellite. And so we can have different objects. We can insert an aircraft and groups of spacecraft and different things. And this is the essence of why STK is called Systems Toolkit as opposed to just Satellite Toolkit. All right, so we can insert a satellite from in different ways. We can start by from the standard object database. We can come here and say, for example, satellite 25544 in the Space Object Catalog is the International Space Station, which we can insert. And lo and behold, we have the orbit of the ISS. It's gonna load real quick. Sorry, it takes a second. And so here you see, hold on, let me turn off this. All right, so here you see the propagated orbit of the International Space Station for one orbit period, and here this is a 3D graphics window, and this is also projecting that motion onto a ground track. And we also have a 2D window, a 2D graphics window, where basically you can see the ground track and the Mercator projection of the motion. And so here, the motion is propagated. We see in the 3D graphics window that the motion is displayed in Earth inertial axes. Here you see the International Space Station coming in, and you see the video. So that's cool. That's not the only way that we can create satellites. We can also create them by defining the orbits themselves. For example, by defining here we have different force models for a satellite that we can do. We can assume a two-body model. We can assume Earth J2 when we're accounting for Earth's oblateness, and we have also high precision orbit propagator and different orbit propagators like that. And what they do is that basically they have different assumptions as to what forces there are on the satellite that you've defined. In this case, we just are going to have a two-body orbit propagator, and where we can say define it in terms of the orbit elements. We also have different flexibility as to the way that we can define the orbit. For example, I can also use the apoapsis or apogee altitude, and we're going to make it something crazy like 10,000 kilometers orbit altitude in the furthest approach and 300 kilometers in closest approach. And you see an orbit with very high eccentricity that we have defined here. So it has very close approach, in a close approach, and very far away approach at furthest approach. So that's kind of the example of what we're talking about. Here we can also change the orbital inclination. For example, this is a 28.5 degrees orbit inclination, which is what we have when we for example have launches from Kennedy Space Center in Florida. We can change this to say 90 degrees, and now we have a polar orbit, which is it's polar because, as you can see, it actually crosses it flies over the poles in each orbit period, over both the North and the South Pole. We can also define this inclination to be 0 degrees, and in this case, the orbit will be what we call an equatorial orbit, which is basically, again, it's the plane of the orbit is the equatorial plane. Other than that, I mean, we have flexibility in a lot of other ways. For example, we can define Again, if we go back to 28.5 degrees for orbital inclination, and we say, okay, let's change the right ascension of the ascending node, which is the point in your orbit when we cross the equator, say that we make that 30 degrees. Now the orbit plane has shifted, and we can make that as much as little as big as we want. And so, as you can see, that's pretty useful because we can essentially define arbitrary orbits at arbitrary times with arbitrary orbit propagators, and that's super general. Um, uh, so what are we using STK for in the SSDL specifically? Well, so that's a good question from Ashish in the audience. So we primarily use STK for preliminary mission design and for studying orbit trades. It's just kind of this interface uh, deal that makes it very useful and very attractive to us. Of course, you can have more precise, or you also can conduct very precise orbit trades because STK has a lot of force models built into it, and we're going to look at that you can basically customize your propagator and do that in a very relatively easy way. I am as a graduate student at the SSDL right now. I'm not using it on my research. The primary use for this is to broadcast this to the community so that they know that this tool is out there that they can use. I personally am not using it, but for example, I was just speaking to a guy in my lab who's using it to conduct thermal studies in the visors mission for not thermal power analysis studies to figure out how much access to the sun he has for his solar panels. So yeah, so in that case, it's very useful. So it's honestly as useful as you want it to be. Okay.
Another point I'd like to add is that the thing with STK is the licenses for unfunded research or educational use only. So if you are going to use on a NASA grant project, you might have to request a license or things like that. There are certain things that you have to talk to OIT about. And there's another one. Aren't there similar analytical software used instead of STK? And is there advantage of using another program other than STK? Ulysses, you want to answer this?
Yeah, so similar analytical software that you can use other than STK, you can use GMAT. That's a NASA provided software. And that one, I believe that actually, I'm not sure what the advantages are. It's actually kind of complicated to use, but it does allow you to bring other high fidelity models like magnetic models and things like that, and it does have integration with the with other NASA interfaces. So are there any advantages of using another programs other than SDK? Really, it's more about licensing and about whatever your research paradigms allows you to use. So it's more of an availability issue. I got a message from Gayatri. Are you able to hear now?
Was able to hear, so maybe it's something on Gayatri's end. Just want to check with others if they are having that issue.
Okay, so okay, cool. All right, awesome. So moving on. So we can also, as I mentioned before, we don't only need to, that we're not only able to see, to create satellites, but we are able to create objects that are attached to a surface. For example, here I'm going to create a place and I'm going to search by address. In this case, let's search Georgia Institute of Technology. So let's look at the first place, and let's look at, we can zoom in our graphics window. Let's take this away for now, make this a little bit bigger. There we go. All right, so if we zoom in, to this place. We are actually on Georgia Tech's campus. Yeah, and this is going to use bank data for 3D modeling of the for 3D visualization of the surface. And right now it's acting. Oh, there we go. So that's actually right by the bus stop, by the Clough building, like right next to Van Leer. Angel, I know that you're joining us from Panama. This is right next to the courtyard in Van Leer and next to the architecture building. So this is kind of cool. This is not real-time data, so none of you should be feeling that we are going to surveil you, but yeah, so you can zoom in and you can clearly see that this is Tech's campus. And this is really useful because if your sensor was attached to a very specific location on Earth's surface, like say an antenna that you have in the back of your house, you can do that, and you can tune like the elevation of it and everything. So yeah, so that's pretty cool. So now what we want to do is we can create a sensor. So let me go back to the view. You can switch back to have a view that's Earth-centric. Let's create a sensor. In this case, this sensor can represent an antenna, a lighter thing, just in order for us to explore what it would mean to have geometric access to it. And this sensor will be attached to a specific place. In this case, we'll put it at Georgia Tech, and you can see that this sensor is a conical sensor and is able to look infinitely out far in space. Now maybe we want to have a more specific constraints as to how far that sensor can go. So let's say that we have a cone half angle of 80 degrees. Now you're able to access that far away. And let's say that our sensor can only access a range of 4,000 kilometers. So we can come back to the sensor and based in constraints, we can say that we have a maximum range constraint from our sensor of 4,000 kilometers. And what we see here is that this, at any one time, our sensor at Georgia Tech is only able to access this region in space. And so if our satellite isn't passing through there at that time, we are not able to access it. And this is pretty, like this already you can see the power of using a tool like STK, because you can immediately see if you wanted to access somewhere on, if you wanted to communicate with a satellite from the Earth, you can see that if that sensor is constrained to be at a specific latitude and longitude, specific coordinates on Earth's surface, and if that sensor has limitations, as all sensors do, then that limits the kinds of orbits that you're able to access. In this case, let's turn on the International Space Station. And you can see that the International Space Station isn't always passing in the field of view of that sensor, actually. So later on, once you have that pass, then you'll be able to see like what regions like you're able to access, and then the next pass you see it gets farther and farther away. Something that you can learn pretty easily from this is that you're on low Earth orbit. In the kinds of orbits that you get from CubeSats that you deploy from the International Space Station, with a sensor like this, you're only able to access them somewhere about 5 to 10 minutes, 3 times a day, every day. So you do not have continuous access to a satellite on low Earth orbit unless you have a worldwide network of sensors. And so that, again, it has a lot of implications that you can immediately visualize for your mission operations concept. Does that make sense? At this point, does anybody have any questions? Cool. So if nobody has any questions, a couple examples I wanted to show you as things that you can see immediately, that you can look at from the using, building this up is, for example, this here is a region of space, a region that we're able to access satellites from. This is, we model a sensor at JPL, and we were looking at a trade study for different rockets, rocket launches for a mission that I was actually looking when I was an undergrad. So you can tell, okay, this is the kind of orbit that I would be able to access if I launch with the Minotaur rocket or with the Neper rocket or with the Antares rocket, or if I just deployed from the International Space Station. And so, like with this, we were able to say, all right, like to get a performance for how much we were able to access, how much time we had from this JP sensor at JPL NASA Jet Propulsion Lab, depending on our launch site. And as you know, the kinds of altitude, the kinds of latitudes that you're able to reach are a function of your orbit inclination, which are in turn a function of the latitude of the launch site. And so in this case, we saw that a higher altitude for the launch was better in terms of access. And you can see these traits pretty immediately. Another thing I wanted to show you is that you can also do trades for your orbit design itself. So in this case, having decided on a sensor at the White Sands center which is part of it's in New Mexico. It's part of the Near Earth network. Using that, we can look at, okay, so what kind of access properties do we have? If we have a sensor at 400, a satellite at 400 kilometers altitude launched from the International Space Station. If we had a 700 kilometer altitude orbit. And so this is kind of the kinds of things you can do in order to say, or to do really quick and dirty trait studies, like cost for a rocket launch versus access and things like that. And so very quickly you can build very complex models just with this basic building blocks. Defining a satellite, defining ephemeris, that is the date and time. And the planetary, the location of the orbit parameters, the position and velocity of your the planet of your choice, and how that affects your mission. And so you can do that just with this basic building blocks, creating a scenario, creating a central planetary mass, and creating a different satellite, creating sensors, and you very quickly can create can track very complex geometries. Cool. So, all right, for the rest of our talk, we're going to create now a different instead of looking at Earth-centered scenarios, we're going to look at scenarios that are based on the sun, for looking at possibly interplanetary orbits. We're not going to save this, and here. So for our next example, we'll look at using other planets. Again, like where this is going to be really interesting. Like this is one of my favorite example applications in STK, to just have the orbits of all the planets in the solar system. So we're going to go ahead and do that. Pretty exciting to me, actually. Okay. So let's again open STK, and before we had the option to choose Earth, and that's what we chose. So now what we're going to do is choose to create a scenario that is centered on the sun. And as you see, you can center your scenario in all kinds of places like Jupiter or Neptune, or essentially any major moon and any major planet in the solar system, including Pluto. Pluto is there too, if you like Pluto. All right, so SASUG, let's call this SASUG tutorial 2. And just for fun, let's say that we're looking at the ephemeris of February 25th of 2025. And you can make the scenarios longer, by the way. This is only 1 day long. You can create scenarios that are a week long and a month old and years long. It's depending on your needs, really. All right, so now this is going to configure the layout, and now we have a scenario that is centered on the sun. This is going to be really interesting. So just give it a minute. Okay. All right, so let's insert a new kind of object. Actually, the planet is not showing here, but we can bring it up. So we can go to Edit Preferences and add the planet object so that we're able to insert a planet. So now let's insert a planet, and let's say that it is Earth. That's our first planet in our scenario. And right now it's not displaying the orbit, it's just displaying actually the sub-satellite point. And this is actually very interesting because you can change your graphics kind of arbitrarily. So in here we go to Earth Basic Definition, and we are going to visualize in our scenario. We want to look at the graphics properties of the scenario. And in 3D graphics, we can say show orbits for planets and don't show sub-satellite points, sub-planet points. And here, there we go. Now we have a one Earth orbit for the Earth. Don't show sub-planet labels either. Okay, so if you zoom out really far, much further than this, the default option in STK is actually going to be to not show up anymore. And the reason is that there's constraints on the maximum orbit that you can show with the maximum size of the graphics window. So you can come here to the graphics and change those constraints. For example, the maximum visible distance, let's make it 10 to the 14 kilometers. That should be big enough. And see, now we're able to zoom in without a problem. Now let's create more planets while we're at it. And so let's say we're going to create, this is going to be, this planet's going to be Mercury. And you see that's Mercury's orbit. And let's create more planets because we're on a rampage here. And we're going to do it because we can. So the sun is right there in the middle. And let's create Venus. And this is actually also a pretty cool example to just kind of see like how big planet orbits actually are. So you can see that Venus and Earth like have kind of comparable distances from the sun, sort of in the same order of magnitude. Now let's get to Mars. And Mars can be pretty far away. Mars, see, like Mars can get like much further away from Earth. It's 1.5 U's, which is 1.5 times the distance away from the Earth. That's like about the Mars orbital radius. And so that's why sometimes we're really close to Mars, sometimes we're really far. And it just depends on the planetary ephemeris. That is the position and velocity of the planets at a given date. And so if we keep going, let's say now, let's say where Jupiter is. Jupiter is so far away, it kind of dwarfs the kind of orbit radius of the Earth. And it gets even crazier the further you go along. Say that we want Saturn. It's in a completely different scale. And if we keep going, Neptune, it's even more crazy. Neptune. to it's kind of hard to fathom just how long the orbit of Neptune is. And this is, I think, like a few hundred years. That's about as much as this scenario propagates Neptune's orbit. It's not even propagating for an entire orbit, which would be like, I don't know, several hundred years. And so, like with this, like interesting example, you get an idea, okay, these are the inner planets, these are like the outer planets, and then the gas giants. So I think that's a pretty interesting example. And so with this, if you keep going this way, you define planets, you define places, you define satellites with their orbits. We can get up to pretty complicated stuff. For example, here I have an example of doing an interplanetary transfer from Earth to Mars. And so, one second. So in this case, please give me a second. All right. So in this case, I'm modeling that in July 4th, 2020, there's a launch from a couple of satellites that depart Earth on that date and that are supposed to reach Mars sometime in February of 2021. And so you can actually play this orbit taking place, and you can, as if it was a video. And so you can fast forward how quickly that happens, and you can see it actually happening very, very quickly. You can see these satellites moving away from the Earth and toward Mars, and eventually reaching their destination. Pretty interesting, huh? And so this is not just for fun purposes, but you can do this for pretty analytical purposes. So eventually, these satellites that I'm mentioning here, they're going to reach Mars, or will they? So here, in this view, we see two different force models. For example, this is J2, just accounting for the oblateness of the sun, and this is sun heliocentric, and this is accounting for third body forces from both the Earth pulling on the satellite and from Mars and from a whole bunch of other planets in the solar system. And you can see here, this is a few days away from actually coming into Mars, and it's like it's actually pretty far away. And in this example, I modeled this Sun J2 body actually reaching Mars on February 18th, 2021. And here, and assuming that at that point it's going to hit the center of Mars. This distance right here is 3.4 million kilometers away from where you thought that you were going to hit Mars, and instead the third body forces and all those other effects, what they did is that they're actually, like, you're not actually arriving Mars when you're supposed to. And this is the rationale for actually doing interplanetary course corrections. And so you can capture these kind of effects with STK, actually, at least from a guidance perspective. Because you have the precise positions of planets, and you have models where you're accounting for the force model. See, from very far away, you're getting to Mars. From pretty close, you're actually not quite getting there. And so this is pretty cool. All the kinds of stuff that you can do with STK. And also, by the way, you can output these kinds of things. For example, orbit position and velocity, orbit elements, axis data, relative geometry to Excel as actual telemetry with time. With timestamps and with values, and you can export them into Excel and do after that with whatever you want. There's also a way to integrate this with MATLAB, where you can just create scenario, propagate, and do all that from MATLAB. I guess another example I had, yeah, I guess that's it for the second tutorial. So let's see. Um, all right, so that's another quick example, and I'm not gonna go into this. Is that in this picture that I'm showing here, uh, something that that you can do for an end of life consideration is say you're doing a planetary flyby, and that's your entire mission. Planetary safety in this case, since you're not actually going to contaminate any planets. Say you're not going to Europa, which is an icy moon. Like what you can do is that you can check, okay, for X many years, say 25 years, you're not going to hit any planets. And it's pretty easy to just propagate it for like about as long as you want and say, all right, in 25 years, 50 years, I haven't hit anything, I'm happy. And so that's what you can do. So, all right, so for the last example, we're going to look at multiple satellites and then the difference that the dynamic models can do in actually changing your like the orbit that you have, and this is the rationale for having more precise models even when you're at the design stage of an interplanetary mission. And so let's go back here and let's create STK, a different scenario. By the way, right now I haven't been saving my scenarios just because those have already been loaded. But if you're working on this on your own, you should save kind of constantly. All right, let's create a scenario, choose a quick and dirty. Let's say suck tutorial 3. All right, so you just gotta wait a minute for it to load. And yep, so back on our familiar Earth, let's create just a standard satellite. Ooh, not a place. We can. By the way, this is the object browser on the right. I've implicitly been talking about it, but you can browse and change every single one of your objects and delete them, copy them, edit them, etc. So here, let's do satellite, and let's just insert a standard satellite. And for now, I just want you to focus on the ground track that we're going to look at. So here, uh, let's just say we're going to have a two-body propagator for this object that has an orbit altitude of about 300 kilometers. All right, so we can see that. All right, so now let's do it again, but instead let's have a J2 force model. So in this case, we're accounting for Earth's oblateness, and we can say, okay, now this satellite, like what's gonna happen if we play this along and say for a day? Is there going to be any drift? Is there going to be any difference between these two satellites? And you see very quickly that they actually start drifting away. Hold on. See, by the way, something that just happened is that I exceeded the time of my scenario. If you want to look at things for a long time, you may want to do like say a month. You can do here, for example, plus 40 days. Now you have a lot more time. So see now, it has been what, a couple days, and already you see that the orbit has shifted significantly. It's distance wise, it's hundreds of kilometers apart. Orbit wise, the orbit plane has actually been rotating, and it is now going backwards. This is called the precession of the line of notes, and this is an effect that we can see very easily, that we can expect, and this is actually something that happens to satellites on the Earth, and we can see immediately, all right, that orbit model that we had, that The two-body model is really not accurate, even in a couple days. And just accounting for one more force term, it's already off the rails. But we shouldn't do that. All right, so now say that we create yet a different satellite. And let's say that this one is going to have about J4 perturbation. And in this case, we're accounting for up to the fourth oblateness term. And see, that one and J2 are actually kind of similar. They're almost right there on top of each other. So that J2 is a really significant term. Now, let's look at this H-pop. And this H-pop is a high precision orbit propagator. And if you can see the force model, this is going to have 21 degrees in the central body for spherical harmonics. It's going to have a drag model that you can adjust. It also is going to have a model that's dependent on the solar flux, on the number of sunspots. And it's also going to have solar radiation pressure, and it's going to take a little bit longer to propagate. And if you see down here, like that's eventually it's going to stop propagating. And see, this is even different from those other two. And you saw the propagation eventually stopped because actually our satellite is losing altitude. Hold on, this is going a little too fast. You can see here on the right and on the left how they diverge. How you start with them going pretty fast and together, but over time, over the scale of just hours, they start diverging and not really sharing the same orbit anymore. So you see how they start diverging, and even after a few hours, it's not the same anymore. You start losing, you start precessing, like your line of notes, your orbit plane starts rotating and going backwards. And then eventually the H-pop is actually going to lose altitude because it has a drag model. It's not a conservative model. It doesn't conserve energy. And so eventually, like what's going to happen is that this model isn't going to tell you, it isn't going to be, it's going to re-enter the atmosphere. So let's say that here we do the 28th of February at that time. We can go on this time and say, all right, one day, not a big deal. One more day, it's drifting more, way more. You see that it's not even in the right side of the planet after a few days. You think that it's gonna be near Australia. Well, it's actually kind of close. Never mind. But hold on. So here you can say 2nd March. A week later, say the 9th of March. It's actually decayed a lot. It doesn't share the same orbit altitude anymore. It has lost quite a bit. And then eventually it's going to re-enter. And it's not going to be valid anymore, and there's no more propagation to be had for that satellite because it's re-entered. And at that point, it just burned up in the atmosphere. And so you can see, like, again, like sort of like the usefulness of STK in allowing you to see these kinds of orbit trades, like right away, and understand, what will happen if I assume that I have a two-body orbit? Is that really accurate? And when you see that it isn't, that can inform your design. And I wanted to close my presentation by looking at this Mars orbit trade study, where this is kind of an integrated model of everything that we've been talking about thus far. So would you say that knowing orbital mechanics in spacecraft dynamics is essential to be able to use STK? I would say that knowing spacecraft dynamics makes you a smart user of STK. It allows you to do it, to make the most of it. You can use STK as a way to help you learn orbital mechanics, and you can use it as a way to kind of check what you know, but yes, and to help your understanding. But in general, yeah. So how do you learn about STK at Georgia Tech, and how do you learn these concepts while learning STK? Well, that's a good question. I took an undergraduate orbital mechanics course before, and what I tried to do with STK is to just replicate what I learned in class and try to see if it made sense when applied to a numerical propagator, and it turns out that it does. So it was kind of reinforcing. And the other thing that really helped me learn a lot about this is that I in my space system senior design capstone project, I had to use this a lot. And so here, for example, you can have different orbits. For example, here you can have a flyby trajectory for Phobos, and that's going to look different than a quasi-synchronous orbit, and that's going to look different than an orbit in which you do aerobraking. All three of those are going to look very, very different. And so you can see, all right, it's the same planet, it's the same target place. Show me what's going to be different about this. And you can say, all right, how long am I going to be able to access Phobos? How far am I going to be from Mars? When am I exactly going to come in? How costly is this going to be? And you can compute all of that using STK. So I personally think that that's pretty fascinating, that a tool like this, it's able to be used with minimal knowledge of orbital mechanics and all these things. So now I know that we're almost out of time, and I wanted to close and say that another capability of STK is that you can have theatrics, actually, that you can have use it to do videos, actually. So and this is like what I'm about to show you guys. I'm gonna share this video about how you can actually use it to do animations and to do videos that can be exported like the ones I showed you. All right, so I guess the video is still processing, so it's gonna take a little bit. Oh, there we go. So let's play this. In this case, we're coming. Oh, this is a really low quality video. I'm sorry. I'm going to just share my screen and do that instead. Just the last thing that we have before we're done. Just sharing the screen. And what you see in this video is actually a satellite that's coming into the sphere of influence of Mars, and it's approaching, and it's coming close, and it's coming. Oh, I'm sorry. Lots of IT problems here. So in this example, like what we see is that the satellite is coming in and is going to pass within about 5 kilometers of Phobos. And it's going to come really, really close. And you can create all these animations, this in focus, out of focus, within STK. So it allows you to even export these things. So it's coming, and boom, it came. And it was a little bit dizzying, but I was, just so caught up in the theatrics of it. And so you can do all of that in STK. So that's it for the tutorial and for the motivation that I had. Any questions?
Thank you, Ulysses, for that talk. I believe we answered some questions on the chat. If there are any additional questions, feel free to put in the chat, and we can answer that for you. Thank you for attending, to everyone, including the ones who had to leave because it's 12 and people might have classes. But thank you once again, and we'll have one more of these. We'll have one or at least two more before the end of the semester.
Yeah, thank you, NASA, for inviting me. I hope it was useful.
Pleasure. Thank you for nice videos and stuff. I didn't know how to use videos in STK. I've never done that. I just do it for my pleasure. So now I can share that with others as well.
Yeah, that's great. That's great. That's great. Yeah, STK is a very, very capable tool. Very capable tool, and yeah. So good to see you all. And if you have any questions, feel free to reach out, and I'll be happy to answer questions.
I think there are. We'll just wait for a minute, and then I'll stop the recording and end the broadcast. By the way, similar to STK, there's another private industry-based software called Free Flyer, which is pretty much like STK, just a competing software. That's from what I've heard is also pretty useful and pretty neat. We don't have a license for that, so I've never tested it, but I have friends who work for Free Flyer, and I've seen videos, and it's pretty similar to what STK does. But once again, it's probably another. You have to get a license and all that kind of commercial software that you have to get licensed and everything for.
Yeah, that's interesting. I had not heard about Free Flyer, so that's good to know.
Yeah, I think they just about 2 or 3 years ago, they're just starting making it more public and trying to get people to buy their software. It wasn't as widely as STK. I mean, I know about STK like from 5, 6 years ago. Free Flyer is like still just getting its word in the map there.
Cool. All right. Well, thanks again, NASA, for inviting me, and I'll see you guys later.
Yeah, thank you, and have a good rest of the week to everyone.
Okay, bye.